Hi, as I promised, I would give you a little review of the conference, and it's just a little review. It's only going to be about 5 minutes long, I hope. What I had to do during the review, if you will recall, is I had to record your data. These are the melting points of various pure samples. I actually had to make those up because I had erased this section. This is real data from a group. Their lowest, their beginning of melting and their end of melting for a 95.5 sample. You can see they're quite varied, but most of them end around 113, 110 to maybe 115 in that range. That would be typical data, 92 to 113. And then this is data for an 85.15 sample. Some things are circled because we were discussing them, but for example, quite a few people end at around 110, 109, around there, okay? This is data for A's, B's, the melting points, and the masses. I don't know if you remember this. Your goal in collecting the first three lanes of data was to create this part of this graph, and I talked about that during the conference. Okay, this point being pure acid analyte, these points being 95.5, and then these points maybe being 85.15. Okay, this would be pure salicylic. Okay. So you're trying to create this graph. This lower point is the beginning of melting, the end of melting. Pure sample melt sharp, lower, upper, first drop to when it's all liquid, first drop to when it's all liquid for an 85.15, okay? So the conclusion we drew, so I'm backing up so you can see that graph a little better. It's not the most perfectly constructed graph. Okay, so the conclusion we drew was that there was a huge standard deviation on the beginning of melting, and this is because people have very different perceptions about what the beginning of melting is. For example, this data here, which is for an 85.15 sample, beginning at 75, and then another person having a beginning of melting at 92, okay? One person having a beginning of melting at 81 and ending at 109, and another person beginning at 88 and ending at 110. So we concluded that the beginning of melting had tremendous standard deviation, whereas the end of melting tended to have less of a standard deviation. Again, this is due to people's perception of the beginning of melting, and some people perceive they really perceive changes in crystal structure, and those are the people that tend to be very, very low, and they are also probably recording the very first perception of sweating or some kind of crystalline change. And the people who are higher, maybe up at 95, they either don't perceive that initial change or they are really writing down the first drop of liquid, okay? So we decided that we could kind of throw that piece of data out and look at the upper numbers. And basically what we did was we checked out whether or not people's upper numbers would work well on the graph. So for example, this is an 85.15. It ends at 109. The corresponding 95.5 ends at 113, and the pure ends at 116. And this would constitute the upper points on this curve. This is what we expect for those numbers to go up. We actually expect the pure and the 95.5 to be closer together because it represents a smaller percentage change than 85.15 to 95.5. A piece of data that would really demonstrate that phenomenon would be, for example, this one, perhaps this, they're actually all kind of spread out. But the first one I did does represent it going from 109 to 113. That's a rather large change to 116, which is a smaller change. Okay, we wrote down a lot of errors that can occur. I'm not going to write them all on the board now. but some of the errors in measuring melting points are just perception. The first time people melt things, they cannot often see what the end of melting is. They're not sure if it's all melted. Packing can affect melting. The sample size has a big effect on melting. There's a gradient in the sample holder, and it gets cooler as you get farther away. So if you have too much sample or dust up in the cool area, you will get a higher end to your melting point. There's calibration issues with the thermometer. The rate at which you heat it has a huge effect on the results. Sometimes people put too little sample in. So we came up with a whole bunch of errors. The ones I think you should focus on the most for the future are the packing, the sample size being 2 millimeters, and your rate being set so that the change in temperature is 1 to 2 degrees per minute during the melting process. This is very important because, again, you don't heat the sample. You do not measure the temperature of the sample. You measure the temperature of the material around it. Then we looked at A and B data, and I'm just going to show you some typical A and B data here. What we expected for sample A, melting point range, we expected sample B, the upper melting point of sample B, to be lower than the upper melting point of sample A. Okay, so another example here. This would be very, let's see, characteristic data. I'm trying to find something that actually falls on the scale here. For example, this one here, it says 112 as the upper melting point of sample B, 115 for A. This one, it's 102 to 109. Okay? And the reason we would expect this is we would expect the A sample to be purer than the B sample, because for most people, the A sample was cooled slowly to room temperature. What this allows is a slow growth of crystals, equilibrium conditions in which the crystal, if it does pick up a salicylic acid molecule, it will have the time to exchange that salicylic acid molecule for an acid-anide molecule, which would presumably have stronger interactions in the crystal and be less easily exchanged. So eventually the crystal would have great integrity and be built in a very regular fashion with the same type of molecule, leading to a much stronger lattice energy. The other issue with growing crystals quickly, of course, is that you form many small crystals, and the small crystals tend to have a large surface area because they nucleated very quickly, and in doing so, they tend to have more material attached to them. Also, the B sample was brought down to 0 degrees, and being at 0 degrees means that it's more likely that the contaminant salicylic acid will exceed its solubility limit and come out. What we expected for the masses is we expected the mass of A to be lower than the mass of B, which was the case for pretty much this whole group. Here's one where the mass is 0.54 for A and 1.02 for B. This is real data from students. We expect this because solubility increases with temperature, okay, with elevated temperature. The biggest factor influencing the mass of material obtained is the temperature and the amount of water used. And I would suggest here that a person who got only 0.54 grams out, compared with, say, someone who got 0.9 grams of out, might have used a larger volume of water. Realize a larger volume of water is similar to being at an elevated temperature, in that more material will stay in solution, including the contaminant. Okay, I'm going to finish this up on a second video, so this is continued on the next video.